Let me welcome you to this lecture. In the last lecture, we have seen how we can do electron counting in case of carboranes as well as in case of metal-carboranes, and thereby predict the structure of this sort of compounds. We will now extend this weights rule for counting of electrons and predicting structures for other types of metal clusters or metal-boranes as well as metal-carbonyl clusters, and also for uh, a special type of clusters formed by heavier main group elements called the Zintl ions. So let us proceed with that, and let us try to find out or do electron counting for a metal-borane first. So the metal-borane, let us do electron counting for B3H7 FeCO3 2. For this particular metal-borane, let us try to calculate the number of electrons. So what we will do again is that we will calculate the number of valence electrons, total number of valence electrons in this cluster, and then we will deduct electrons which are not used for skeletal bonding. So first we have 3 boron centers here. So 3 into 3 for each boron center. Have 3 electrons in the valence cell. So total 9 valence electrons from the 3 boron centers. There are 7 hydrogens here. So this gives us 7 valence electron. We also have 2 iron centers. So 2 Fe. So each of these iron centers have 8 valence electron in their valence cell, and that is why 16 valence electron from the 2 iron centers. Now the carbonyl ligand, we will take it. We will not count electrons for the carbon and oxygen separately. Instead, we will take electron donated by the carbonyl ligand essentially all together, and that we know that each carbonyl ligand donates 2 electrons to the metal center, and that is what forms the metal ligand carbonyl bond here. So 3 carbonyl centers, 6 carbonyl ligands total, because this group is present 2 times. So 6 carbonyl ligand, total 12 valence electron from the 6 carbonyl ligands. That's what we get over here. So let us count the total number of valence electron in this cluster over here. 9 plus 7, 16 plus 16, 32 plus 12 is 44 valence electrons we get. Now we will have to deduct the electrons which are used for non-skeletal bonding purposes. So that we know that all of these 3 boron centers will have 3 terminal hydrogen atoms, and we have to deduct the 2 center 2 electron terminal pH bonds, or electrons used in the 2 center 2 electron terminal pH bonds first. So that is 6 electrons from the 3 pH bonds we'll have to deduct from the total valence electrons. Apart from that, we will also have to deduct electrons for the for this particular metallic fragment, because metals, if we see that this transition metal like iron have total 9 orbitals are present in a metallic atom over here. It has one, say for iron, it has one 4s orbital, and then 3 4p orbital, 4p 3 orbitals, 4p orbitals are present, px, py, and pz, and there are 5 d orbitals, 5 3d orbitals are there in the valence cell of the iron center. Now we have seen earlier, we have discussed earlier that a boron center, say a boron atom, uses 3 of the sp3 hybridized orbital for skeletal bonding, while 1 of the sp3 hybridized orbital is used for formation of 2 center 2 electron BH bonds in boron molecules. So what appears from here is that for formation of these polyhedral skeletal structures, one needs only 3 orbitals for each of these atoms, and the rest of the orbitals can be used for other types of bonding which are non-skeletal bonding essentially. So since iron has total 9 valence orbitals here, 1 s orbital, 3 p orbital and 5 d orbital. So such transition metals have total 9 valence orbitals, and out of these 9 valence orbitals, only 3 orbitals are going to be used for polyhedral skeletal bonding, and the rest of the orbitals will not be used for polyhedral skeletal bonding. Instead, they will be used for binding with the ligands. Here, the carbonyl ligand acts as a terminal ligand, and these some of these electrons will be used for binding, which for forming terminal iron carbonyl bonds, while the rest of the electrons will reside in orbitals which are non-bonding in nature. So, what we will do is that we will deduct for each transition metal center only 3 orbitals are required. Iron will use only 3 orbitals for formation of skeletal bonds, and the rest of the 6 orbitals in the iron center will be either used to form bonds with ligands, used for non-skeletal bonding. So some of these orbitals will be used for forming bonds with terminal ligands like carbonyl ligand in this case. So iron center forms terminal iron carbonyl link 3 terminal iron carbonyl linkage in this particular fragment FeCO3, while the rest of the uh, orbitals will be there as non-bonding orbitals. So in these total 6 bonding and non-bonding orbitals which are used for non-skeletal bonding, essentially 12 electrons are going to be present. So 12 electrons are going to be present in these orbitals. So for each of the metallic center, what we'll have to do is that we'll have to deduct 12 electrons from the total valence electron count. For every metallic center present, we'll have to deduct 12 electrons which are going to be used for non-skeletal bonding, and only the rest of the electrons which are going to be present will be used for skeletal bonding there. So because there are 2 iron centers here, we will deduct 2 into 12, 24 electrons for these iron centers, for these 2 iron centers from the total valence electron, and when we deduct this from the total valence electron, that is 6 electrons for the 3 BH bonds, 24 electrons for the 2 iron centers, the remaining number of electrons will essentially be used for skeletal bonding. So 44 minus this is going to be 30, so that is 14 skeletal electrons. So in this particular cluster, the skeleton is essentially formed by 14 skeletal electron, which translates into 7 skeletal electron pair, and these 7 skeletal electron pair, or the polyhedron that is going to be formed from this 7 skeleton electron pair, we know is going to be an octahedron, because here by using Wade's rule we know that for formation of a polyhedron with n vertex, n plus 1 skeletal electron pairs are required. Here we have the total number of the n must be equal to 6, and only then we will have this n plus 1 7 skeletal electron pairs are present in this cluster. So the number of vertex we obtain is going to be equal to 6. And now let us see the number of atoms which can occupy the vertex in this octahedral structure predicted by electron counting. So number of vertex atoms. There are 3 boron centers which are going to occupy the vertexes, while the 2 iron centers from these iron carbonyl tricarbonyl fragments are also going to occupy the vertexes. and that is why total 3 plus 2. So 5 atoms are going to, 5 of these vertexes are going to be occupied for in the octahedral structure. So that what we have is a, from the electron counting we can predict that we have a nido structure as one of the vertex remain empty. So let us draw the structure of this. We can so what we can do is we can place the this boron. So 3 of the hydrogen are used as terminal pH hydrogen atoms, while the rest 4 hydrogen atoms are going to be present as bridging hydrogen atoms here. In this particular fashion, it is going to be present. So that is how we can say that we can predict the structure of this metal-borane cluster by using Wade's rule. We will now extend the Wade's rule to predict structure of non-borane clusters. We can use the Wade's rule quite successively to predict the structure of metal-carbonyl clusters as well. So let us try to find out the structure of a metal-carbonyl cluster by using Wade's rule here. So the metal-carbonyl cluster that we have chosen for this purpose is rhodium 6 carbonyl 16 here, and again we will do total valence electron count and then deduct the electrons which are not going to be used for skeletal bonding, and then there that will essentially give us the number of electrons which are going to be used in skeletal bonding, and from there again we can find out the basic structure or the polyhedral structure of this cluster compound. So we have 6 rhodium. Rhodium is a group 9 element, and there are 9 valence electrons in rhodium. It is a cobalt group element. So each of these rhodium atoms have 9 valence electron. So 6 into 9, which is equal to 54 valence electron from the 6 rhodium centers. So then we have 16 CO, and the 16 carbonyl groups are going to, each of these carbonyl are going to provide 2 electrons. So what we have is 32 valence electron from the carbonyls. So this is going to be equal to 6, and this is 86. So what total we have 86 valence electron in this metallic cluster, carbonyl cluster. So now we will have to deduct electrons which are not going to be used for skeletal bonding, and we have already learned that for each of these transition metal center present we have to deduct 12 electrons, because 6 of the orbitals out of the 9 orbitals in the transition metal are not going to be used for skeletal bonding, and there will be electrons in those, and electrons in those orbitals we'll have to deduct from the total valence electron to obtain the number of electrons which are going to be used for skeletal bonding. So 6 rhodium we have to deduct, that is 6 into 12 non-skeletal electrons, which is equal to 72 electrons So when we deduct these 72 non-skeletal electrons, what we have here is equal to 4, and this is equal to 14, electrons are essentially skeletal electron here, which translates into again 7 skeletal electron pair. And from here again what we can say is that the number of vertex here is equal to 6, and the number of atoms occupying the vertex each of these rhodium centers are going to occupy one vertex. There are 6 such rhodium centers. So all the 6 vertex of the polyhedron here, that is an octahedron, we know are going to be occupied by a rhodium center, and the structure is going to be closure here because all the vertexes are essentially occupied, and the structure is going to be closed structure. And we can draw the structure as well. That is, we can place rhodium at each vertex of an octahedron here, and that way we will have the basic polyhedral structure of this rhodium carbonyl complex. Now we'll have to assign the carbonyl centers here to the rhodium atoms, and what we'll have to do is that we can divide this molecule, or we can write the formula of this compound as RH. For 6, there are 16 carbonyl groups, so each of the rhodium centers can have maximum 2 carbonyl ligands as terminal ligands. So we can write this as 6. So then we have accounted for 12 of the carbonyl centers, carbonyl ligands, and 4 of the carbonyl ligands will be present as bridging carbonyl ligands, which are not going to be terminal carbonyl ligands. So what we'll have now here, each of the rhodium centers, we attach 2 carbonyl ligands as terminal carbonyl ligand. And we have assigned all, now we have assigned all the terminal carbonyl ligands to each of these rhodium centers, and now we'll have to draw the 4 bridging carbonyl groups, and these bridging carbonyl groups are attached to 3 carbonyl rhodium atoms. So they exhibit mu-3 coordination mode, and they are at the center of each of these opposite triangular faces, one bridging carbonyl ligand is present. So this is one triangular face of the octahedron, and the opposite triangular face for this triangular face of this is actually over here. So that is another carbonyl ligand, and then we have also one carbonyl ligand over here, bridging carbonyl, and then another bridging carbonyl ligand on this triangular face over here. So that is the structure of RH6CO16, and that we can predict by using electron counting, using the weights rule. So in this way we can predict the structure of metal-carbonyl clusters as well by using the weights rule. We will now see another very interesting class of clusters whose structures can be predicted by using the weights rule again. And these clusters are formed by the post-transition elements. When we dissolve the post-transition elements in ammonia in presence of sodium or alkali metals, then we reduce these post-transition elements to form anionic clusters known as Zintl ions, essentially. Zintl ions. So examples of such Zintl ions is Pb5 2 negative or Sn9 4 negative. This sort of Zintl ions with interesting structures are well known. Now we can predict the structure of these Zintl ions as well by using the Wade's rule. Again, what we will do is that we will calculate the electrons, total valence electrons, and then we will deduct the electrons which are not going to be used in skeletal bonding, which will give us the electrons that are used in skeletal bonding, and from there we can find out the structure of such clusters or Zintl ions. So let us do the calculation for this particular Zintl ion here. So we have, so lead is, we know, is a carbon group element, so there are 4 valence electron in lead. So 5 Pb, lead essentially give us 5 into 4, that is 20 valence electrons are there from the lead ion or lead centers over here. Then we have 2 negative charges are there in this cluster, so that is 2 electrons from the negative charges. So 22 valence electrons total are present here. Now we'll have to deduct electrons which are not going to be used in skeletal skeletal bonding again here. So again, what we know here is that for lead, the valence orbitals are s orbital and 3p orbitals, total 4 orbitals are present here. Total 4 valence orbitals are present, and out of these 4 valence orbitals, only 3 we need for skeletal bonding, and one of these orbital is not going to be used in skeletal bonding. So we'll fill 2 electrons in this orbital which is not going to be used in skeletal bonding. So this leaves us 3 orbitals with 2 electrons in these 3 orbitals, and these 2 electrons are going to be used in skeletal bonding for each of the lead center over here. So for each of the lead center, we know 2 electrons lie on an orbital which do not participate in skeletal bonding. So what we'll have to do is that for each lead center, we'll have to deduct 2 electrons from the total valence electron count, and that will give us the number of electrons which are going to be used in skeletal bonding. So we have 5 lead centers. So 5 into 2, that is 10 non-skeletal electrons. So once we deduct this, what we get is 12 skeletal electrons are present in this lead cluster or lead Zintl ion over here. So that gives us 6 skeletal electron pair, and number of vertex is equal to 5 here, and number of vertex atoms again is equal to 5. There are 5 lead centers here. So this is going to be a closure structure, and the structure of this Zintl ion we can now draw is going to be trigonal bipyramidal. So that is the structure of this Zintl ion, that is Pb5 2 negative. It has a closure structure and trigonal. The lead ions are essentially placed in the vertex of a trigonal bipyramid. So let us now try to predict the structure of Sn9 4 negative by using Wade's rule and using similar methodology here. So we'll have count the number of electrons, valence electrons here. 9 S-team centers are there. Again, tin is also carbon group element, so we know that for each of these 9 tin centers we have 4 valence electrons, so total 36 valence electrons from the 9 tin centers, and we also have 4 negative charges here, so which again gives 4 electrons. So this totals out to be equal to 40 valence electrons we have in this cluster, and we will again deduct the electrons that are not going to be used in skeletal bonding. And again we know tin also has 4 orbitals, 1s, 3p orbitals, and out of these 4 orbitals only 3 orbitals are going to be used in skeletal bonding, while another orbital is going to remain non-bonding, and this orbital we will place 2 electrons in this orbital, which will be present as lone pair of electrons here in this case. And for 9 of these tin atoms, we will have to deduct 9 into 2, so that is 18 non-skeletal electrons. So when we deduct 18 from 40, what we have is equal to 22 skeletal electron. So this translates to be 11 skeletal electron pair. So now we know the number of vertex is going to be 10. What we have, the structure is based on a decahedron here, and the number of vertex atoms is equal to 9. So only 9 of the vertex are occupied by the tin centers, while 1 of the vertex is left empty. So that is why the structure is can be classified as a nido cluster, and the structure can be, we can draw the structure. So that is the structure. We see that this structure looks like nest-like because one of the vertex of the decahedron, that is the structure is based on, is essentially not occupied by any tin center, and that is why it is going to be a nido structure. So this is how we can also predict the structure of Zintl ions by using Wade's rule, and this brings us to the end of this lecture. Essentially what we have learned during this lecture is how we can do electron counting for metalloboranes as well as for metal-carbonyl clusters, and also for Zintl ions, and how we can find out the number of total skeletal electrons in such clusters by deducting the number of electrons which are not used in skeletal bonding, and from here we can predict the structure of these clusters successfully. So let me conclude this lecture with this, and I thank you very much for being with me during this lecture.